All right. Welcome, one and all, to chapter 24 of Earth History for Philander University. In this lecture, we will be discussing stars, space, and galaxies, the formation, evolution, and possible eventual demise of these things. This is, again, part of the astronomy section of the Earth History class. We started out with geology, transitioned a bit over into hydrology, then the atmosphere, and now we've left the Earth, right? Um, as I've said with the previous astronomy lectures, this goes far more, actually, every chapter. This goes far more in depth. I'm going to touch. This is very surface level conversation to be had. If you have any questions or comments at anything discussed here, please feel free to leave them in the comment section down below. I or a fellow classmate can try to tackle them. With that all being said, let us begin. In the beginning, right? That should sound familiar to some of us. Did the universe have an origin? Well, that's an interesting question to ask. You could say it always existed with no beginning, or you could say it began at a specific point in time. Those are kind of your two options, right? In 1929, Edwin Hubble, that name should sound familiar, observed that all galaxies were moving away from one another. By applying these motions, he surmised that a common starting point and therefore starting time must have happened at some point. This was eventually dubbed the Big Bang Theory. If everything's expanding out at some point, we would assume they came in together. All mass was at a literal point. As we've discussed, and as you probably heard in previous physics classes, matter cannot be created nor destroyed. So, all the matter that exists must therefore have been existing throughout time. And if all matter is expanding out, that must mean in the past the matter would have been closer and closer and closer. Closest thing you can get is a point or a singularity. Calculating back from these galaxies, we get a starting point of around 13.7 billion years ago, meaning the furthest away galaxy we see is some 13.7 billion light years. So that light takes 13.7 billion years to reach us. Therefore, it's been traveling 13.7 billion years. Here is a very common outline you see of the proposed Big Bang, starting from time zero, with a point of infinite density and you don't even have a temperature because everything is at that certain point. Within the first 1/100th of a second of the universe's expansion, radiant energy throws out neutrinos, electrons, positrons, other various fundamental particles at ridiculously high temperature. Over time, these subatomic fundamental particles condense down to form protons, neutrons, helium, deuterium, atoms, what have you, over the first couple 100,000 years. As time continues on and on and on, these atoms coalesce into protogalaxies, primeval galaxies, and quasars, and then finally, from about 14 billion years ago to now, modern day galaxies. And another thing to point here is the cooling of the universe over this time from unimaginably hot to the modern chilled universe that we have. Very brief, skipping over a lot of detailed mathematics, physics, what have you, but that is the general consensus that we have. As you can see, the chemistry of these reactions, 4 hydrogen nuclei fuse to form helium, along with 2 electrons, and tremendous quantities of energy are released in this process. This is this step up here, the protons to the helium to the atoms, over the first 300,000 some odd years. Within those first 300,000 some odd years, about 10 minutes in, that's referring to if you consider the universe to be a calendar. I don't think we touched that, sadly. I should add that. Helium starts to cool from primordial nucleosynthesis, and trace amounts of lithium are forming. Lithium, of course, being the three protons, third element in the periodic table. No nuclei larger than this exists. So you don't have carbon, you don't have nitrogen, you don't have oxygen, etc. The very beginning of the solar system, you have hydrogen, helium, and you're starting to get lithium slowly but surely. By about 300,000 years old, all had cooled the elements to a few thousand degrees, and electrons start to stick to the nuclei, if you will. Your electron clouds start to form due to the energy being reduced down. This is evident from the cosmic background radiation. The expected original photons, if you will, that radiate about 2.7 Kelvin, a temperature that has been mathematically predicted. A lot of what we're talking about here was predicted to be true via the calculations if this stuff happened, and we later on find evidence asserting those calculations, those predictions were accurate. That's one of the fun things about this, the fact that we can look back 14.4 billion years into the past and have a general understanding of what went down. Again, the math checks out. I'm not going to go too deep into the math here, obviously, but comment down below if you'd like some links to understand this further, and we can have that conversation. The universe is what we call non-homogeneous. Essentially, it's lumpy. The universe isn't some flat plane like you think about. It has spots to it, it has galaxies, it has stars, which are in reality planets, clumps of matter. The matter being those original hydrogen, helium, lithium, what have you. The really young universe had waves of energy that became these clumps of matter, those waves of energy being, of course, this guy here, the resultant of the fusion of atoms together to form higher elements. And these waves give us the cosmic background explorer, found by the cosmic background explorer COBE, and have been noticed. Here we have a three-dimensional computer-generated drawing of a portion of the universe. And again, we notice the unevenness of the matter distribution. This is what's to be expected given the understandings of the explosions of the Big Bang. And this is also what we witness, which again is a cool collection. Energy from the Big Bang was the first generation of energy. Light from the original origin spreading out, right? And that from that light, we see stars and galaxies in the second generation of energy, or light from the concentrated matter from the atoms coalescing. Over time, this matter coalesces, forming nebulas, huge clouds of hydrogen and helium. This coalescing, this bringing together of the atoms, gravity starts playing a role here. The more stuff you get, the more stuff wants to hang out together. Gravity can cause these nebulas to collapse in on themselves. If the nebula is big enough, we're talking gigantic scales here, this falling in of this gravity could start fusion reactions themselves. So you have the hydrogen and helium smashing together, forming fusion reactions, and then the positives that smashed together initially clump together due to gravity, causing, again, fusion reactions. Fusion energy releases energy that flows out. The gravity of this fusing pours more mass into it. And it is this balance of pressure and compression that essentially allows a star to exist as a star. Stars fall into very strict parameters of size, luminosity, intensity, what have you. The diameter and density of a star are determined by two opposing forces, the gravity pulling particles inward and the energy from fusion reactions in the core forcing the particles outward. This will make more sense when we go over the life cycle of a star. Here's a very famous image, right? The Pillars of Creation. The Hubble Space Telescope has provided a close-up view, and other telescopes have provided a close-up view of stellar nurseries in, for example, Orion's Belt. The pillar-like structures here are about 3 light years tall, really big, given that the sun is about 8 light minutes away from us, to give you a scale here, and are composed of cold gas and dust. Energy from nearby stars and shockwaves from exploding stars have concentrated the gas in the pillars and initiate star formation. These are star factories you're looking at. And this is a real image. It's, the color has been altered to make it more presentable, but that's an actual picture you're looking at there. That's not an artist representation necessarily. And over time, these things have actually changed and altered, which is another really cool aspect of it, right? These are constantly undergoing flux. So the sun, our sun, it's pretty large, right? 2 times 10 to the 30th kilograms. It's pretty massive. About 109 times the diameter of the Earth. Pretty big. Within its core, there fuses about 4 million tons of hydrogen a second. That's a lot of action, right? It's about 15 million Kelvin. You don't say degrees, 15 million Kelvin, about 150 times as dense as water, giving you a 140,000 kilometer diameter and enough fuel. The sun has enough fuel to burn for 5 billion more years. That's how massive the sun is. That's how massive this game is. As with usual, I don't stop to detail these particular question slides, but I do stop so you can pause them, answer them yourself before we continue. Here is a sketch, if you will, of the different layers of the sun. Fusion, of course, occurs at the sun's core, which we talked about previous. And the energy escapes first by radiation out of the core, this radiative zone. And then convection, which is the touching, the heat transfer via touching something, out here into the convection zone. And then we enter out here about 500 kilometers thick or so, the photosphere. And that is the thin layer that we actually see. The sun is not, just like the Earth, the sun is made of concentric layers that not necessarily look like what's on the surface. Of course, outside of the photosphere, you got the chromosphere, the light emission from that, and then a corona of energy spanning out, giving you the breadth of the sun. To go into more detail here, the radiative zone is the dense gas that's outside of the core that is producing all the energy. And the convection zone would be a high temperature differential from top to bottom layers that takes the heat at the core and spreads it out into the outer layers. The chromosphere is an example of one of these outer layers, a diffuse gas layer above the photosphere that is 2,000 to 3,000 kilometers thick, and you can actually witness the chromosphere during a solar eclipse. And then there are flame-like jets and all these other things, sunspots, what have you. The outer layer itself is what we call the corona, a tenuous gas layer beyond the photosphere that essentially appears as a blue halo during an eclipse and is really, really, really hot. Within it are heat strips. The heat strips atoms into ions and electrons. That is the source of solar wind. As those atoms are broken apart, energy is released from that. And landing us eventually at the photosphere, the solar atmosphere, if you will. Some 400 kilometers thick at 5,700 Kelvin. It is core heated with a glowing gas that gives us essentially our sunlight, a somewhat granular structure. And here is where, of course, we see our sunspots, right? Again, the photosphere is what you see when you look at the sun. There you go. A close-up of the sun's surface showing that granular texture that I talked about. There's actually a super high res picture of the sun that I believe was taken in 2019 that is worth looking up on your own time. Seeing this granular nature in high definition is really weird looking. Each small bright yellow dot is a rising column of hot gas about 1,000 kilometers in diameter. And the darker reddish regions between the dots are cooler descending gas. So, right, things are starting to form circles, right? How does the Earth heat? The core is very hot, giving off radioactive decay, rising energy, and the mantle convection currents. That sounds similar to what we're looking at here, doesn't it? During solar eclipses, the photosphere is blocked by the moon, thus giving us thin red streaks beyond the moon's outline, which are portions of the chromosphere, and the larger white zone is that corona we're talking about. When the moon blocks the sun at that dang near perfect degree during the solar eclipse, the sheer brightness of the sun is diluted a little bit, allowing us to see details you wouldn't usually see otherwise. Or if you look at different spectrums, you can see this stuff. Again, look up the sun. It's a fascinating nearby friend of ours. Here we have a prominence rising some 500,000 kilometers above the photosphere. This is the stripping of the atoms into the ions, what have you, the solar winds, and it's miraculous looking. So that was our sun. Let's just go from our sun and do stars in general now. Stars are initially cataloged just by brightness. Apparent brightness, i.e. luminosity as seen from Earth. And since that's one way to define brightness, you need to take distance into account. Further away something is, the dimmer it is. We understand this concept. You can, however, look at absolute brightness, which is essentially how bright the actual star is, or its brightness at about 10 parsecs or 32.6 light years away. The scale is set with our sun as a value of 1, because our sun is the sun we know the best. If a sun has an absolute brightness greater than our sun, it's a higher number, less than our sun, lower number than 1. This allows us to look at the Hertzsprung-Russell diagram. This one's interesting. It shows our main sequence stars as sinusoidal lines along which about 9% of stars lie. The luminosity and temperature are directly related to one another, and larger stars are essentially brighter due to greater gravity driving more fusion reactions. Here we can see, as said, that the main sequence star comprises the vast majority of stars that we get. Our sun is an average size sun at about 6,000 right here. Okay, growing yellow. The hotter, and again, look at the temperature rises to the left and luminosity rises up. So up here, these blue stars are very large, very blue, right? The hot flame is blue. And then over here, we've got cold, super large stars, the giant stars, which are red, a cooler temperature. And then down here, little teeny white dwarfs, which can be blue dwarfs, which can be very, very hot, but are very, very dim. This graph here describes all stars that we see. That's very interesting to look and see how stars are related, and the combination of temperature, luminosity, and these interesting curves that appear on it. The sun size is related to helium nuclei fusing into, hydrogen nuclei fusing into helium. The helium cannot fuse into heavier elements at the temperatures that we have. And as fusion slows, the temperature drops, the outward light pressure drops, and the star contracts. If the star contracts, the core heats up as a result of this, the increased gravity, and the heat ignites hydrogen fusion in the outer layers. The outer layers are going to expand and become a red giant. The jump from main sequence to these guys over here. Pictured here, I'm going to read this off because this has written does, I think, a better job than me pontificating off the top of my head. Evolution of a star. At maturity, A, the energy in a star, the size of our sun, for example, is derived from hydrogen fusion at the core. B, when most of the hydrogen in the core is consumed, the star starts to contract, as we talked about, right? The star starts to contract. Then expands the hydrogen fusion as hydrogen fusion starts at the outer size. So you've got the core shrinks in here, the helium core shrinks in, and the outer part expands out. In the red giant phase, gravitational coalescence in the core and hydrogen fusion on the outer shell produce hundreds of times as much energy as was produced when the star was mature. The star contracts again when the helium fusion initiates in the core, and the 4 parts in this diagram cannot be drawn to scale. Keep that in mind, as the star's diameter varies from 1.2 million kilometers to 160 million kilometers. Massive scale difference. Also, in all cases, the core has been drawn larger to show detail. So these images show an idea of what's going on, but they cannot, by definition, in any way, shape, or form, be drawn to scale. And this is what happens when this star expands out to this star. Luminosity increases, effective temperature decreases because the engine at the center is running out of gas. As I said, the core of the star shrinks during a red giant until the helium fusion starts out. Once the helium fusion starts, it fuses into higher elements such as carbon, and eventually the helium will run out. The further contraction causes, again, heat gain. This cycle appears here. And at one solar mass, solar being sun, one solar mass, pressure does not cause any more fusion. When you run out of that fusion, this blows the gas shell straight off because you're no longer having the gravity being able to fight that outward pressure. That gas shell being blown off forms what we call planetary nebula. It contracts to about the Earth's size or so and glows from residual heat, thereby creating itself a white dwarf. So tens of billion years, the white dwarf runs out of energy and goes dark. So the sun contracts and expands as its energy is essentially dying out, the gas is running out. Eventually it contracts so much that the gravity fuses the core into higher elements such as carbon and what have you, and then blows itself up in just spectacular creation of a planetary nebula. When it blows up, the remaining elements of the star continue to burn out as best they can in a white dwarf, and eventually turn into what we call a black dwarf and die out, giving you this weird chain reaction going through the 6 stages of the sun's life cycle. This is for our sun in particular. Keep that in mind here. So it started out with the gas and dust we talked about, entered the protostar phase of the collapse of the energy. We're currently in main star sequence. Go team here. Eventually, it'll oscillate around as a red giant before exploding into a planetary nebula and end its life cycle as a white dwarf as it eventually dies out. Here we have a ring nebula that is a sphere of gas and dust expelled by a dying star. Here's an example of the future of our star and of it part of the universe. We nowadays, as a recording of this slideshow, I guess I should say, are in step 3, but we can look at step 5 out there in space. Cool. And this lines up with the math that this chart follows. Well, that's our star. What about stars with greater than 1.44 solar masses? What about stars that are larger than our stars? In this case, the carbon fusion initiates and iron forms, an even higher element than what our star makes. The iron fusion absorbs energy and the star cools very fast and rapidly collapses. We're talking the order of seconds for the star to collapse in on itself. This collapse induces a massive heat buildup. I'm talking trillions of Kelvin. And this causes the star not to collapse in on itself, but to actually explode in what is known as a supernova. The shockwave from this explosion causes fusion reactions that create the rest of all the elements. The higher elements that exist, such as iron, we know about platinum, what have you, are the result of gigantic star explosions. And that's fascinating. Here we have the 2 ways things can go. The main sequence star, our star's planet here, or larger stars that go red giant explode. And if they're high mass stars, they turn into neutron stars, which we'll talk about. And if they're very high mass stars, lots and lots of matter in this main sequence star, you actually get black holes and supermassive black holes, and the story goes on and on and on. Here we actually witnessed, cool enough, 1987, a supernova explosion. Thank God they put this arrow here, otherwise you wouldn't notice the boom that happened in the sky. During this explosion, the star actually became the brightest object in that portion of the sky. We saw a star explode. The star existed, exploded, then didn't exist. First and second generation stars went under the same processes as they originally were only formed from hydrogen and helium, so those are only 2 things that exist. Some of these old population 2 stars do still exist, oddly enough, because they were large enough to keep on burning. When the star dies as a nebula or supernova, the dust and gases form into new stars. But these stars then contain heavier elements, and thus the newer population 1 stars contain small bits of these heavier elements. And our own solar system is in fact the result of this recycling that I'm talking about here. The universe is 4.7 billion years old. Our solar system is, what, little over 6.5. So you had half the universe, half the time the universe has existed, our solar system did. This process has been ongoing that entire time, building elements, building the building blocks that eventually landed us on this wonderful little planet. After a supernova, there is often a very large mass left over. We call that is larger than a white dwarf. This is the result of the subatomic particles that we've been talking about previously squeezing together. Electrons and protons, create neutrons, what have you. These densely packed neutrons can form what we call a neutron star, a stupidly dense star on the order of 1,000 kilograms per cubic centimeter. That's really heavy. Sometimes these form into pulsars, which are spinning neutron stars that actually give out regular spaced radio waves. You can catch these using radio telescopes. A spoonful of a neutron star is about as heavy as Mount Everest, to give you an understanding of that density. It is beyond the scale of understandable how big these things are. And here we have that pulsar I was telling you about, that rotating neutron star that happens to sweep past detection of Earth and give us this blinking signal. Very cool stuff. The math and the science behind this stuff is quite astounding. Again, comment down below. I can lead you towards some interesting videos, papers, books, whatever you find interesting to do. So those are neutron stars and pulsars. What's a black hole, right? A black hole happens to stars that have more than 5 times our sun's mass. When these die, the leftover core is so massive that even the neutrons themselves collapse. Neutron stars happens when the protons and electrons collapse, but what happens when the neutron collapses? This compresses to a point mass, or what we call a black hole. A collapsed spot that is so incredibly dense and the gravity is so incredibly strong in this location that that light itself gets pulled down into it. They're hard to find by definition because we can't see them. So we have to look for co-orbital bodies, something rotating around the black hole that is affected by something we can't find its dance partner. Or we can look for hot X-ray sources, where X-rays can't escape the edge of the gravitational field. Here's an example of the dance partner that we're talking about. An ordinary star that's getting its energy sucked into a black hole. Black holes can exhibit gamma ray bursts, gamma rays being the highest energy in the EM spectrum, right? That are about 10 million times as energetic as sunlight. Longer bursts likely come from exploding stars, and shorter bursts may come from neutron stars. And this is part of the action that forms a black hole. And we've witnessed these things, right? So that's a bit about stars and star life. Let's transition over to galaxies real quick. In the 1850s, better telescopes showed that some stars had interesting or odd shapes to them. You essentially had elongated pinwheel stars, what we now call galaxies. Usually about the most common galaxy is a spiral type, the Milky Way, what we live in. But about a half of these spiral galaxies are called barred spirals. And then there are galaxies that actually don't have patterns, or very odd, unusual patterns. Very interesting stuff. Here's a barred spiral galaxy, NGC 1365. That is displays a conspicuous bar running through its nucleus. This guy here, right? Why is that? There's a lot of fun math and science involved behind those things. So now we're talking about galaxies. How do galaxies move? Well, we understand those via Hubble's law. Galaxies can be shown to be moving away from each other and from a common center. The most distant are moving the fastest, and the closest are actually moving slowest. We calculate this difference via redshift, which we talked about previously. Hubble's law states that the velocity of a galaxy is directly proportional to its distance from Earth. The further you get, the faster you go. Our sun lies in a barred spiral some 200,000 light years across. the glowing plane of stars in the night sky is what's known as the Milky Way. I'm sure you've seen the bright streak at night. Do we have a? I don't only have a good picture of it. I'm sure you've seen that bright streak of stars. That like that bright swath that's a bit more intense in the night sky. That's actually the Milky Way galaxy looking at that point. And it contains some 400 billion stars. A spherical halo of dust and old stars surround our galaxy. And these fringe stars occur in globular clusters. This right here is kind of what the Milky Way galaxy looks like. Within this galaxy, there's, as I said, some 400 billion stars, and we're like right there. We are the tip of this, that little dot right there, that pixel. That's probably not accurate enough to indicate our location. That's how big the Milky Way galaxy is itself. So we are 8 minutes from the sun. The Milky Way galaxy is 1,000 light years tall and 100,000 light years wide. Massive in scale. Absolutely stupidly massive in scale. The center of the nucleus of the Milky Way galaxy cannot be directly observed. We are on the edge, and we need to look through this to see what's in here. Can't actually look at it. It's too difficult. But we can use X-ray, radio, and infrared imagery to suggest we can use that, and that suggests to us there's a large, almost donut-shaped core that puts out some 10 to 80 million times the solar output of energy of our sun. This mass is rushing back into a donut hole and then possibly ejecting during explosions. What's going on at the center of the Milky Way? Good question, right? The Milky Way appears as a band of light, as I discussed before. However, this light's actually produced by billions of stars in the plane of the galactic disk, not the gas itself, but the stars in the Milky Way is what's producing this light. The very center of our galaxy holds something, the Great Attractor, it's usually called, that's about some 3.6 million solar masses. We therefore assume it's a black hole, given how big it is and how it's able to keep everything spinning around it, essentially. This is a galactic nebula. We exist in a galactic nebula, a large dust or gas cloud. Within that, you have emissions nebulas and absorption nebulas, essentially hot and cold gas clouds that behave, interact with each other within a Milky Way. This bright region shown in this picture in the center of this image is a small but powerful radio source from the center of the galaxy. You're looking right there, you're looking 27,000 light years towards the center of our Milky Way galaxy. Gases falling from the center produce red, orange, and blue streamers. Look at the shape of these things as they're spiraling out. Pretty interesting. All right, so that's our Milky Way galaxy. Let's move on to other weird things in our solar system. We'll start with quasars. Quasars are objects discovered by emitting radio waves that emit radio waves rather than visible light. Weird. You can't see them with your eye because they don't emit visible light, but they do emit energy on different parts of the EM spectrum. They are very, very far away and very, very red shifted. Excuse me. Sorry, I got to sneeze. Okay, there, I got the sneeze out. That took a while. So, quasars, very far away, very red shifted. Their effects so far, as they are so far, they yet still emit strong signals. They're very far away, but we still get very strong readings from them, which means they're very large, very powerful. Some 8 to 12 billion light years away, we assume these quasars formed when the universe was young. Since it takes, right, the universe by definition is 14.7 billion light years wide, because that's how fast the light had to travel. Something that's 12 billion years away, that's within the first, 2 to 6 billion Earth, billion years of the solar system before our solar system itself was created. Here we can look at quasar 3C275.1. This is the brightest object near the center of the photograph, or this doodad here. An elliptical gas cloud surrounds this nucleus, and the quasar is about 2 billion light years from Earth. The smaller objects in this picture, these little dots here, are regular galaxies. So this is a bunch of galaxies. Remember, galaxy is this. Galaxy is not the sun and Mercury, Venus, Earth, Mars, what have you. That's not a galaxy. This entire thing is a galaxy. And this image, all these dots, all these energy sources are considered galaxies. This dude here, look how big he is. But it's a quasar, so it doesn't emit visible light. Fascinating stuff about the universe, right? So we talked at the beginning about the universe started at a particular point. Well, if it starts someplace, does that mean it ends someplace? The Big Bang caused an expansion of the universe, and as we know, gravity pulls on an object everywhere, gradually bringing things together. Does that mean that the universe eventually closed, that gravity will eventually win and everything will collapse in itself one day? Or are we essentially going to beat gravity out, have an open universe where things fly apart and eventually fusion stops? Both those two have a stop point to them, right? Because suns blow up, suns create, when a sun blows up, the particles fly everywhere, right? Does that mean every single particle is then recoalesced into planets and suns? No, by definition. Eventually, you're going to blow up so many times, you're not going to be able to recoalesce again. Open universe concept. Here are two systematic representations of the possible cosmologies. A, the closed universe model, and B, the open universe model. Essentially, we're seeing that here, the Big Bang, things expand out. Eventually, things get so far away as they stop moving out and gravity pulls them back in, condenses down, and 1 and 6 look very similar, don't they? However, the open universe model says we're going to beat gravity out eventually and things can be separated out of the way. Recent data implies the universe may not only be open, but also accelerating. However, time will tell. More data is required to figure out which of these two options is likely to happen. Is the universe slowing down or is the universe speeding up? What sort of force acts to make the universe change how fast it expands? Now we get into the fun conversation of when we look at the size of the universe and the apparent weight of the universe, we can only count for about 4% of its total weight. Some 23% of the universe is thought to be dark matter, which is matter that has regular gravity to it, but we can't see it. The gravity exists, but that's the only way we can measure it is via gravity. It's not releasing any sort of EM spectrum. And beyond this, some 73% of the universe is thought to be some dark energy, which causes a poorly understood repulsive force. We witness things happening that we can't measure beyond the simple fact that they're witnessed. So we come up with the concepts of dark matter and dark energy to kind of fill that void. Will eventually these concepts be better understood? It's very possible. And that's the fun of this, right? We lie at the end of a chain of quite literally improbabilities. Initial temperatures and expansion rates, mass ratios of protons and neutrons, the ratios of gravity, electromagnetic forces, strength of nuclear forces, mass of electrons. All these things are clicked together to form the universe we have, the sources that we have, the planet that we have, the human that we are. And it's quite fascinating, right? If any of these were appreciably different, who knows what the universe would look like? It sure as heck wouldn't look like what we have now, because that list of those constants gave us the universe that we exist in now. fun stuff. I hope you like this conversation, right? This is a very much a starting introduction to this topic. It is very deep. If you have any questions, comments, please leave them down below in the comment section so we can have a conversation on it. Thanks for watching. Take care and stay safe out there.